So here is a polynomial expression that I'd like for us to think about what it would mean to factor this expression. So first of all, what's the first thing that comes to your mind looking at this expression and thinking about if we're successful in factoring this, what we're supposed to get is a way of understanding it as one expression times another expression. So what are the first things that jump out to you as what should we be thinking about in order to get us started in this process? One of the first things we might think about are the exponents. So in this expression, I've got one term with an exponent of 4 on the x, another term with an exponent of 3. What exponent exists on this x? 1. It's a little hidden secret 1. So let's make it not hidden anymore. Let's pull back the curtain on Oz there and give that an exponent of 1. Okay, great. So that means that each one of those 3 terms has some x's in it. Right? So let's think about what it would look like to make a factor tree out of all those x's. If I'm going to factor x to the 4th, according to what we talked about last time, I can think of x to the 4th as being what I get if I multiply x to the 1 by x to the 3. By the way, why is that? Why is it the case that if I multiply x to the 1 by x to the 3 that I get x to the 4? What's happening there? You add the exponents because we are doing what to the monomials? Multiplying, right. Multiplying monomials with the same base, we add the exponents. So x to the 4th can be broken apart into an x to the 1 times an x to the 3. But then in turn, the x to the 3 can be broken apart. Let's say I break it apart into an x to the 1. What would I have to match with that x to the 1? X to the 2, exactly. Again, because multiplying monomials means that we add the exponents. X to the 1 times x to the 2 is going to get me back to x to the 3. And then for my last step, factor my x squared into x to the 1 times x to the 1. Right. So we can kind of treat these variable factors here, these powers of x, we can treat them just like they're numbers and sort of build out a factor tree for them. I'm going to erase the powers of 1 here. And in this viewpoint, we would kind of stop right here, and we would say all these x's that are at the bottoms of the branches of this factor tree, those are kind of taking the place of our prime factors, in a sense, right? X to the 4th, we're saying, is, at its basic heart, x times x times x times x. That shouldn't be too much of a surprise. That's how we define x to the 4th power in the first place. If we do the same thing for the other powers of x up here too, and this is not a step that you're going to do every time, but I want to do it now because I want us to think about the ideas here. X times x squared, and the x squared breaks apart into an x and an x. And so x cubed factors into 3 factors of x. And then I have x to the 1st power, which we actually can't break apart at all. Right, so it's just a single power of x. So now my question is going to be, among all 3 of these powers of x that are represented in our polynomial, what do all 3 of them have in common in their factorizations? What's the most that the 3 of them have in common? X to the 1st, right. So my term at the end here has an x to the 1st that also the other 2 share. Right? But if I try to tack on any more x's, so my first term here has another power of x that the second term also has, but my third term doesn't. Right? So the most number of x's that all 3 of these terms can agree upon is a single power of x. And we have a name for that. We say that so first of all, that x is a factor of the monomials x to the 4th, x to the 3rd, and x. It's a factor of all 3 of them, and so we call it a common factor. And because we can't stick any more x's in here without it no longer, in fact, being a factor of this last one, we not only call it a common factor, but we call it the common factor that we cannot exceed. We can't make any bigger. It's called the greatest common factor, which is a mouthful, so it's often abbreviated GCF. So the greatest common factor of these three monomials, x to the fourth, x to the third, and x, is x. Does anyone, by the way, see a shortcut? Without having to write this factor tree every time, how could I have looked at these three monomials and known that x is the greatest common factor? What's the quick way, Christina?
Because it's the least, it's the smallest number.
Yes, it's the smallest number where?
Of the like terms.
Yeah. It's the smallest number that's in the exponent, right?
Yeah.
So x to the fourth, x to the third, x to the first, it's the smallest exponent is going to give us the greatest common factor. So that's something that you can take to the bank on that. X to the first. It's the smallest exponent which is a little bit counterintuitive because it's the greatest common factor, but it's the smallest exponent. So either remember that that's backwards, or the better explanation is that the word greatest is not what's important here, it's the word factor. And factor always implies that we're taking something that's smaller than the original quantity. And so if we want the greatest common factor, we want that exponent which all three of these have in common, which is going to be the smallest one. So we know that our greatest common factor for these three terms is going to have only a single power of x in it. I want to put one more conceptual frame on this. And I think we've seen this a little bit before, but here it comes again. It's a little multiplication grid. I think last time we looked at this, I claimed that it sort of comes from the new math, the sort of Common Core math, although this frame has been around for a long time. The idea here being, last time we used this, we used it to multiply. This time we're going to use it to factor. 18x to the fourth minus 12x to the third plus 30x to the first. And what we've just said is that we are going to aim to factor out a single power of x from each of these three terms. So I'm going to put that kind of out front over here. Okay, and then in my final answer, up here at the top, I'm going to put this single power of x right here as the variable factor in my first set of parentheses, x to the power 1. Okay. All right, so we've cracked the nut on the x's. Let's try and add in our coefficients. So the numbers 18, 12, and 30. How am I going to figure out what those have in common with one another? So now I want to know what's their greatest common factor. Does anyone see this off the top of their heads? I'm going to be brutal about it, but if you see what it is right now, holler it out. Greatest common factor. So 3 is definitely a common factor. 3 goes into 18 6 times, into 12 4 times, into 30 10 times. So 3 is a common factor, but is it the greatest common factor, Joe? 6. So 6 goes into 18 3 times, 12 twice, 30 5 times. Is 6 the greatest common factor? Kishel's nodding her head. Yeah, it is. And one of the ways that we can tell that, by the way, is that the number of times 6 goes into 18, 3. The number of times 6 goes into 12, 2. The number of times it goes into 30, 5. 3, 2, and 5 have nothing in common with one another. So there's no way to get anything else in common from the 3, 2, and 5 to tack onto the 6. So yeah, 6 is our greatest common factor. If we wanted to do that systematically using a prime factorization, we could. We would just go ahead and find the prime factorization of each of these three. So 3 and 3, and then a 12 breaks into a 2 and a 6, and the 6 breaks into a 2 and a 3. And 30 breaks into a 2 and a 15, and the 15 breaks into a 3 and a 5. And so then I would go looking across all the prime factors at the ends of the tree branches and say, well, all of them have a 2 in common. So we know 2 is going to be a part of our greatest common factor. All of them have a single 3. But then once we've accounted for the 2 that they have in common, and the 3 that they have in common, we can't find anything else, any of these other prime factors, that we can use that's common to all 3 of these. Because 3 from our first one is not shared by the second and third one. The 2 from our second is not shared by the first or the third, and our 5 from the third is not shared by the first or the second. So the best that we can do is the greatest common factor of 6. So again, that's the systematic way of getting that done, 18, 12, and 30, is 6. And so when I add the coefficients into my monomials, the greatest common factor is going to get a 6 out in front of it. And so now I'm going to add that 6 in front of my grid. I'm going to add it inside of my first set of parentheses. And now I know what it is that I'm going to be able to factor out of this polynomial. So in principle, once we've figured out what it is that we're going to factor out, we've won most of the battle, in principle. Now our job is to fill in the rest, figure out what belongs here. Often I will call that the cofactor. So the thing in the front, factor, this thing's a cofactor. It goes with the factor. And so to do this, let's just take one of these examples here. We have to ask ourselves, how many times does 6x go into, I don't know, for example, let's take the one in the middle, 12x to the third. Negative 12x to the third. So how would you answer that question? How many times does 6x go into negative 12x to the third? What kind of thinking do you do? Okay, so Spencer, tell me about your answer. You said negative 2x squared.
6 times negative 2 is negative 12.
Okay.
And it's already got an x on it.
It's already got an x, so it only needs how many more?
2.
2 more. Okay, right. So you're treating it as what's called in the business a missing factor problem. You're asking 6 times what is going to give me negative 12, and x times what is going to give me x cubed. And so in your mind, you're filling in each of those blanks. This one's a negative 2, this one's an x squared, because we add the exponents. Right, so that's treating it like a missing factor problem. Another way we can think about it, and that way works just fine, and that I think that's the way that a lot of people do these problems. Every missing factor problem is also a division problem in disguise. So another way to do it, that's even a little bit more systematic if you like this way, is just to divide. Negative 12x to the third divided by 2x, because we did division problems like this on Monday. Right? How many x's do I end up with? How many powers of x do I end up with when I do this division? 2. Because why? Exponents subtract when we are dividing monomials, right? So we know we're going to end up with x to the power 2, and then the coefficient, negative 12 divided by 2, I'm sorry, I meant for this to be a 6. Negative 12 divided by 6. That gives me the negative 2. So you can see it either way. You can just treat it as a straightforward division problem where we know that subtracting exponents because we're dividing monomials, or we can treat it like a missing factor problem and sort of do the backwards thinking in our heads. Either way, we'll get to the same place. So negative 2x squared is the missing cofactor for that middle term. And we'll just do the same thing for the others. So how many times does 6x go into 18x to the fourth? So 6 goes into the 18 3 times, 18 divided by 6. And how many powers of x? 3. Yep, because x to the fourth divided by x to the first is x to the 4 minus first. So 3x to the power 3. And then to finish with our 30x to the first, how many times does 6x to the 1 go into 30x to the 1? 5 times, and how many powers of x do I want there? None. So I could, if I wanted to, write x to the 0 here. What is x to the 0?
0.
Now is the time when we get the 0 power discussion. So, okay, before I put this x to the 0 here, you told me that I didn't really need it. Right? Your first answer was just 5. So what do we call a number which it doesn't matter if we multiply by it or not? Because I agree, we can write it or we can not write it, and we get the same answer. So what number, what's another name for the number which when you multiply by it, or if you don't multiply by it, you get the same answer? 1. There are 2 kinds of nothingness in arithmetic. One of them is 0. 0 is the kind of nothingness that doesn't change anything that it's added to. 1 is the other kind of nothingness that doesn't change anything that it's multiplied with. And so that's the kind of nothingness that we get when we raise something to the 0 power. So often people will just conceptualize this as any number Any non-zero number raised to the 0 power is always equal to 1 for any non-zero x. And you might ask me, why non-zero x? Well, it's a longer story. That's a calculus story. So maybe in a couple semesters you can get a full answer to that question. For now, I'm just going to leave that one. I'm not going to touch it with a 10-foot pole today. But that completes our factoring problem. 3x to the third minus 2x squared plus 5. And we took a lot of extra time to explain each individual step. As you get more and more practice with this process, you'll be able to automatize a lot of the reasoning that we just did. But for today, I think it helps to unpack it all, see it, all of it in its detail, and kind of explain where each of the parts of the process comes from. Think about it in a couple different ways.